Now we're going to talk about how to use the correlation coefficient to make predictions. If you find that there is at least some correlation, more than just a very small one, between x's and y's, you can use that correlation and the fact that you know x's in order to predict y's, which may not occur until later. Often standardized tests are designed to provide predictors of something like future college performance. Well, our task is really to find the best fitting line to our points. If we had a scatter plot with a number of points on it, and it led us to believe that there is a linear relationship, then our task is to find the best fitting line for all those points. The best fitting line is the one that's going to give us the the smallest squared deviations from that line. Every point is a deviation from that line unless the point falls right on it. Our criterion for the best fitting line is the one that gives us the smallest deviations squared and summed up. You can come up with all kinds of lines to fit these points, but the best fitting one is the one that gives us the smallest sum of all these squared vertical deviations. We'll talk more about that later. For now, it's just a matter of coming up with a formula for the straight line. You probably learned the formula for a straight line. In fact, I'm sure you did. You may or may not have used exactly the same notation that I learned. But y equals slope times x plus the y-intercept. Our task is to find the slope and the y-intercept of this best fitting line. It turns out that it's not all that daunting a task. The formulas, which are actually fairly simple, simply give us the best fitting slope and y-intercept. Our notation's a little different. We talk about a predicted y. We let b stand for the slope here and not the y-intercept as you may have learned it. And then a stands for the y-intercept. So we need to find slope and y-intercept for this best fitting line. Slope is pretty easy. If we've already computed Pearson's R, we already have the sum of cross products and the sum of squares of x. We simply plug those, numbers in again to get the slope. The sum of cross products was 14 in our example using these numbers, and the sum of squares of x was 20. And that gives us a slope of 0.70. All we need is a y-intercept now. Y-intercept is found by taking the mean of the y values from our sample and subtracting from that the slope that we just figured times the mean of the x values. Well, the sum of our x values was 25, and if you divide by 5, you get a mean of 5. The sum of our y values was 70. If you divide 70 by 5, you get a mean of the y's of 14. So we have 14 minus 0.7 times 5 as the y-intercept. And if you work through that, it comes out to be 17.5. Let me go ahead and do it. 14 minus well, I think I made a mistake, so let's do work it out. No, that's right. 14 minus 3.5 is 10.5. So, to get any predicted y value, all we have to do is plug our x value into this formula. So let's take an example. Let's say we have a subject who has a raw score of 10. Actually higher than any of the x values that I have here. So what would the predicted y value be if this person has a score of 10? 0.7 times 10 plus 10.5. 0.7 times 10 is 7 plus 10.5. This just seems too simple, doesn't it? We get a predicted y of 17.5. As I say, we could predict y's for any different x value that we might obtain. Not such a tough task. Turns out the tough task is evaluating just how good these predictions are, and we'll take that up in another module. But what it really amounts to is, when we make predictions like this, what kind of errors do we get in our prediction process? We have to actually compute something called the standard error of estimate in order to do that. It's kind of like, in fact it actually is, a standard deviation of errors in prediction. That's later.